Hello, good morning everyone. This is Mr. M from Algebra Lessons. In this video, I am explaining DeMoivre's theorem proof by the help of Euler's theorem. In the last video that I posted on YouTube is explaining Euler's theorem, and before that I uploaded a video for DeMoivre's theorem separately. But here we are going to connect those two. Probably that proof may be an interesting one. Okay, but before I'm going into this proof, I just want to refresh your memory with some basic concepts of complex numbers. Okay, for every non-zero complex number for every complex number x plus iy, we can express this complex number in the form of r of cos theta plus I sin theta. Okay, we can express this in the form of r of cos theta plus I sin theta. You actually may heard these terms called the polar form of a complex number, the polar form, and the rectangular form. Okay, so we are actually trying to express a a regular complex number x plus iy in the form of r of cos theta plus I sin theta. So when we are considering this, because this is an equation, we can rewrite this as x plus iy is equal to r of cos theta plus I sin theta, and FOIL it, r of cos theta plus I into r of sin theta. So x plus iy equal to r of cos theta plus I into r of sin theta. And guys, you can simply equate the real and imaginary part of this equation. So our parts will be like this: x is equal to r cos theta and y is equal to r sin theta. Okay, that's good. And our actual objective with DeMoivre's theorem is to find the nth root of a complex number, and that nth root is specifically based on the angle it is creating in the complex plane. Okay, so that means our primary objective in all of the problem that we are going to discuss under this particular concept is to figure out the degree measurement of the complex number, or the degree measurement it is creating in the complex plane. That means we need to figure out what is this theta. Okay, from these two equations we can easily figure it out. So how can you do that? For doing that, just divide these two equations. So this is equation number 1, this is equation number 2. So if you can divide these two equations 2 by 1, so 2 by 1, the equation will be y over x is equal to r sin theta over r cos theta. Just plugging the values. R got cancelled out, so y by x is equal to tan theta, implies tan theta is equal to y by x, or y over x, and therefore from this we can write theta is equal to tan inverse of y over x. So that means we found the value of theta that is satisfying the given complex number which is situated in a complex plane. So this theta, okay, this theta is very important. That is the angle angle made by the complex number in a complex plane. And with respect to that theta, the position of the complex number is changing. Okay, the position of the complex number is changing, and so that only we are actually saying that theta is very important for all complex value problems. Okay, and now this tan inverse y by x we can prove using a small example. It's not an example, it's a demonstration of a complex number. So let it be, give me a moment. Okay, so if I have a complex plane like this, okay, suppose I am considering a complex number 2 plus 2i. Okay, so this is 1, this is 2, this is 3, this is 1, 2, 1, 2, 1, 2. It's going on like that. So because this is a complex plane, we will name this as the a real part or the real number, and this is the imaginary number. Okay, so how can I plot this complex number? That is very important. 2 is the real part, so in the real axis you consider 2. This is 1, this is 2, so 2. And what is the imaginary part? So 2 itself is the imaginary part, so go up 1, 2. So this is the point of this complex number 2 plus 2i. So suppose I'm joining this with a line to the origin. This is actually that complex number, that line representing the position of the complex number. And see, if I'm making a right triangle by drawing a line to the x-axis, see what this represents. This represents the x-axis. Okay, x-axis. And what this represents? This represents the y-axis. Okay, and the angle theta it is making with the baseline or the real axis is this. So that is angle theta. Okay, so basically we are actually trying to find out the length of this complex number, or yeah, we are actually trying to find out the length. So length means the distance of from this point to this point. Okay, if this is a right triangle, so this is a right triangle. If we have a right triangle with its base x and altitude y, we can use the Pythagorean theorem to calculate the length of this. So that is why this will become square root of x square plus y square. Just for understanding, I explained those concepts. That is actually not needed for our proof. These are actually the items I just want to define, or I just want to explain in advance or in the beginning of this proof, just to refresh your memory. That's it. Okay, so and before we are going on to the proof, I just want to say a little bit more about this theta. Here we have theta is equal to tan inverse of y over x. So with respect to the value of y and x, the amount of theta, the amount of angle making in the complex plane is changing. Oh, okay. So whatever the value of x and y, we will have infinitely many values for this theta, correct? So x can y choose any values. So with respect to that value, we will get a value for theta, that is the angle. And the peculiarity, so the next 2 points you have to remember for the future problems. The peculiarity of that theta will be all theta values will differ by the multiple of 2 pi. Okay, differ by the multiple of 2 pi. So that is the first thing. And second thing is, even though we have values which is differing with the multiple of 2 pi, we will have a value. We will have a value, specifying a value in between negative pi or minus pi and plus pi. Okay, negative pi and positive pi. That value, that is theta, is in between negative pi and positive pi. This value of theta is called the principal value. The principal, sorry, my handwriting is not looking good there. So principal value. Principal value. So for the calculation problem, for the calculation issues, or the problems that you may discuss in your class with respect to the root of a complex number, sometimes it may be the cube root, square root, whatever it may be, the nth root. In common, it's the nth root. When you are calculating the nth root of a complex number, principal value has its own role. And if you know what will be the principal value, we can use that for a successful completion of your problem. Okay, so then theta is called the principal value of the argument. And how can we express that? The amplitude of this complex number x plus iy, amplitude of the complex number x plus iy can be written as tan inverse of y by x. So amplitude means what? Amplitude means the angle made by the complex number in a complex plane. So so we can say that the amplitude of the given complex number will be the tan inverse of the given two sides, or the tan inverse of the quotient of the imaginary and real part of the given complex number. So that is actually the very basic. I just want to explain in advance before we start our proof of this proof of this particular theorem. Sorry, taking much time to get some space. Otherwise I can do something just like clear my canvas. That way I will lose my space, or I lose my writings that I did before. Okay, so those are the basics. So I'm not worried about whether it is lost or not. So we can start our theorem. Okay, so DeMoivre using Euler. Okay, so we can start the proof. Okay, what is this DeMoivre's theorem stating? DeMoivre's theorem stating that if n is an integer, whether it is positive or negative or it's a fraction, cos theta plus I sin theta to the power n is cos n theta plus I sin n theta. So that is actually the statement of DeMoivre's theorem. Okay, how can we prove it? Okay, so because we are proving this statement using Euler theorem, we may use some external ideas for the proof. Okay, as per the exponential theorem, we can write e raised to x is equal to, what is e raised to x as per exponential theorem? It is 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. So that is the exponential theorem statement. Okay, we have the real tool. Now we are going to play with this. So I'm going to replace x with two complex numbers z1 and z2. Okay, we can try with this. This is the real tool. Okay, z1 and z2. Okay, so when this x is z1, what will be our exponential statement? So that will be e raised to z1 equal to 1 plus z1 plus c1 square by 2 factorial plus c2 square by 3 factorial plus etc. Oh, okay. Then what is the statement if it is z2? So e raised to z2 equal to 1 plus c2 plus z2 square by 2 factorial plus c3 square by 3 factorial plus etc. Okay, now we have two statements of exponential. That is actually kind of a version. Okay, because we actually changed the variable x into the form of a complex number. So now I am just asking you to find the product of these two. Okay, you can do that. So then what will be e raised to z1 times e raised to z2? Interesting question, because this is a series. So 1 plus z1 plus z1 square by 2 factorial plus z2 square by 3 factorial plus etc. times 1 plus z2 plus c2 square by 2 factorial plus c3 square by 3 factorial plus etc. Okay, so because this is a series, we can choose the very few members in the beginning of this series. So when you are foiling this bracket, the result will be like this: 1 plus z1 plus z2 plus c1 square by 2 factorial plus z1 z2 plus z2 square by c2 square by I made a mistake, not c1 square by 2 factorial. Yeah, yes, it is c1 square by 2 factorial. So c2 square by 2 factorial. Yeah, that is correct. That is correct. I also made a problem in between the foiling process. So and so on. Okay, so this is the thing, and we are actually going to conclude at this point. So this is, let me try to use a different color. Okay, this is 1 plus c1 plus c2 times, and see here we have a 2 factorial in the denominator. Here also we have a 2 factorial. So the same 2 factorial, if I am multiplying the numerator and denominator, I can take the whole 1 by 2 factorial outside. So plus 1 by 2 factorial into, this is c1 square plus this is 2 factorial means 1 into 2, 2 z1 c2 plus c2 square. So z1 square plus 2 z1 c2 plus z2 square is c1 plus c2 the whole square. Okay, plus etc. That means 1 plus z1 plus c2, okay, plus c1 plus c2 the whole square by 2 factorial plus so on. So see, when e raised to z1 times e raised to z2, we actually concluded here 1 plus z1 plus c2 plus z1 plus c2 the whole square plus 2 by 2 factorial plus etc. See, this is actually in the form of 1 plus x square by 2 factorial plus etc. See, what is this 1 plus x square by 2 factorial plus etc.? This is actually representing e raised to x. Okay, then what will be this? This will be e raised to z1 plus c1 plus c2, because x is c1 plus c2. So we proved e raised to c1 times e raised to z2, e raised to c1 plus e raised to c2 is e raised to c1 plus C2. So this is actually the cornerstone of this particular proof. Okay, and if you continue like that, e raised to z1 times e raised to z2 times e raised to c3 times etc. means kind of n terms. Suppose n terms we are considering, n terms is, how can we write that? This will be is equal to, we are concluding this extension from this proof, so the product will be can be expressed as the sum of exponents. So this is e raised to c1 plus c2 plus c3 plus etc. n terms. Okay, and so we can make this into small piece, like e raised to instead of writing z1, z2, z3, z4 etc. n terms, I am assuming c1 is equal to c2 is equal to c3 is equal to c4 is equal to etc. The nth term will be equal to c. So I can write this as e raised to c to the power n. Those many z's are there. Okay, so this is equal to, what is this? E raised to z1 plus z2 plus z3 plus etc. nth c. Okay, we have n c's, so we will write the sum as e raised to n c. See, now look into this. E raised to z the whole to the power n is equal to e raised to n c. What it is exactly the rule of exponents with a power. Okay, I'm actually not stopping here. My video is continuing like this. If z equal to I theta, let us assume z equal to I theta. Okay, so what will happen? So then this equation will be e raised to I theta to the power n is equal to e raised to n into I theta. That means e raised to I n theta. Oh, okay. Something is smelling, correct? What is this e raised to I theta? We know that from the Euler theorem, we know that e raised to I theta is equal to cos I theta plus, cos theta plus I sin theta. Cos theta plus I sin theta. This is e raised to I theta by Euler theorem. That means if this is e raised to I n theta, e raised to I n theta, this will be cos n theta plus I sin n theta. So this is actually the DeMoivre theorem. We can rewrite this as e raised to I theta to the power n. Okay, e raised to I theta to the power n. What is e raised to I theta? E raised to I theta is cos theta plus I sin theta. So this will be to the power n, that's equal to cos n theta plus I sin n theta. So this is actually the proof. So I believe all of you enjoyed this proof, and I believe you will be ready for another video. And so to get another video that I am uploading on YouTube, please subscribe my channel and don't forget to press the bell icon. And thank you very much for watching my video. See you soon.